everyone. I know we are approaching the last part of the day, so your energy is probably going down, but I hope you still have some spare attention for us, because today Manolo and I are going to talk about a very interesting and important topic: the waste heat recovery systems. Now, I would like to start actually asking you a question. Is there anybody here that has already installed any energy recovery system in his plants of any kind? One hand, two hands, maybe? So very few. So I guess, no, you don't count, except you. Okay, so I guess this is the right session for you. As you probably know, there are several parts of a steel plant where you can apply energy recovery solutions. But today our focus will be on the waste heat that can be recovered from the electric arc furnace. It's well known that there are mainly two types of energy input in the electric arc furnace. Of course, the electrical energy and the chemical energy. If we consider that these two contributions provide the 100% energy input in the furnace, the interesting information is that 25–30% of this energy gets lost in the primary fumes. And this is a really significant number. So, let's try to recover all this energy. But actually, it's not that easy, and mainly for two reasons. The first one is that if we are tempted, for example, to recover the chemical energy contained in the primary fumes, trying to recover the CO, for example, this is actually not really feasible because due to the process itself, as you know, the CO content in the EAF primary fumes is very low. Different story compared to what happens, for example, in the converter plants. And then the second reason is that the EAF process is very discontinuous. So also the recoverable energy is discontinuous. So what can we do? Well, we need to focus our attention on the thermal energy that is contained in the primary fumes, trying to recover as much as possible of this energy. And then we need to overcome the discontinuity of the EAF process by designing a plant that is capable of mitigating the discontinuous process of the furnace and the variability of the energy that is contained in the fumes during an entire heat. But how can we recover this thermal energy? The waste heat that is contained in the primary fumes can be recovered in the fume treatment plant, in particular from two parts of the primary fumes line: the cooled parts and an heat exchanger that can be placed downstream the cooled parts. Basically, what happens is that the heat is transferred to a cooling media that at the end of the process inside the waste heat recovery systems can be transformed in hot water at low pressure and low temperature, typically 90 degrees, in hot water at high pressure and high temperature, typically 200 degrees, or saturated steam. Now, one of the most useful outputs among these is actually the steam, as it is one of the most flexible media that has several applications inside and outside the steel plant. And this is the reason why Danieli has developed the Q-Steam system. And here is Manolo that will explain you how this system works.
Yes, thank you, Alberto. Let's have now a journey inside the steel making plant with the aim to better understand how the system works. Our target is to achieve a more sustainable steel production, of course, and this is obtained not only controlling the environmental pollution, but also optimizing the energy consumption. Thanks to the heat recovery system, the Q-Steam, it's possible to recover part of the energy contained in the primary fumes and transform it into saturated steam. The flexibility of the Q-Steam system allows to recover energy from two different parts of the fume treatment plant primary lines: the radiative part and the convective part. The radiative part are basically the cooling equipment of the fume treatment plant primary line, while the convective part is the heat recovery boiler. The starting point of the Q-Steam system is the feed water tank. is a biphasic tank where oxygen and CO2 are removed from the feed water, thus preserving the lifetime of the different components. The degassed water is sent to the last part of the heat recovery boiler, the economizer, where it's treated before entering into the steam drum. The saturated water contained into the steam drum flows via natural circulation to the pipe bundles of the boiler in the so-called evaporator section. The increase of the water temperature leads to the production of steam, creating a water-steam mixture that flows back into the steam drum. Part of the water contained in the steam drum is sent to the cooling circuit of the fume treatment plant, the cooled part of the primary suction line. Then the thermal energy contained in the primary fumes is transferred to the water that flow inside the membrane walls, thus allowing the production of steam. The Q-Steam system is equipped with a steam accumulator that acts like a storage tank, compensating the discontinuity of the EAF process, providing a constant steam flow rate during an entire heat. Then the steam can be directed to the user inside or outside the plant. Inside the plant for vacuum degassing, RH, pickling line, steam turbine, organic Rankine system turbine, or outside the plant for district heating, for example, or electrical power plant. Please, Alberto.
Thanks. So, this is the Q-Steam, Danieli solution for the recovery of the heat contained in the EAF primary fumes and the steam generation, with a special design to mitigate this continuous process of the EAF and provide to the different users a constant supply of steam. One of the key features of the Q-Steam system is its flexibility, that allows to choose different configurations according to the different customers' necessities and also to the specific necessities of each plant, especially when we have to deal with revampings of existing plants. In particular, it's possible to recover the energy from the cooled parts only, the heat recovery boiler only, or both from the cooled parts and the heat recovery boiler. As you can imagine, this last configuration is the one that maximizes the energy recovery, allowing to reach up to 70% of recovered thermal energy. But you know, theory is nice, but it's always better to see real numbers. So let's have a look together to an application. Here we have a 195 tons electric arc furnace. You can see also the main process data, like the tap-to-tap time, power on, the charge mix, and so on. But the important numbers here are the ones related to the inlet and outlet temperature of the primary fumes in the waste heat recovery system. As you can see, we are going from 1200 degrees down to 250 degrees. It's quite intuitive that the configuration we have adopted here is the one that maximizes the energy recovery. So we are recovering the energy from the cooled part and the heat recovery boiler. Well, with Danieli Q-Steam system, we can produce 60 tons per hour of steam. This is a good number, but it's actually worthless if we don't understand the real benefits coming from this number. So think about this. If we have to produce the same amount of steam with a standard boiler fed with natural gas, considering the capex and the opex of the standard boiler with natural gas compared to the ones of Danieli Q-Steam, the return of investment of Danieli Q-Steam system is approximately 2 years. And this is the real important number.
So, I think we said many times during this presentation, but an important plus of the steam as output of the system are the many applications that it can have both inside and outside the plant. So, just to recap, to summarize, inside the plant, the steam can be used for vacuum degassing, RH, steam turbine, pickling line, or organic Rankine cycle turbine. And outside the plant, as we said, for power plant or district heating. But If the final purpose of the thermal energy recovery is only the electrical energy production, there's no need to have a more structured and, for some aspect, more complicated plant like the one for the steam generation. In fact, for this specific case, there is another effective way to recover the thermal energy, and this is by generating hot water instead of steam. With hot water, the plant is simpler and, of course, cheaper, while the difference in terms of efficiency is almost the same. And this is the concept behind our energy recovery system for electrical energy production, the so-called clean heat recovery system, and this is explained in our video. In this specific project, the fumes coming from the electrical furnace inside the fume treatment plant primary line are directed to an heat exchanger, a water fuel heat exchanger, where the hot water circulating inside the closed circuit is heated up to a temperature of 220 degrees. Then the hot water is sent to the organic Rankine cycle plant, but first passing through a thermal stabilizer, where the discontinuous temperature of the water is stabilized to an average value of 200 degrees. And now the stabilized water is introduced inside the ORC evaporator, where the organic fluid evaporates and passing through a turbine is generating electrical energy. This plant is a plant that has a production of 1 megawatt of electrical energy, since it refers to the organic Rankine cycle system installed in ABS plant, and it has worked for around 5-6 years.
Okay, thank you, Manolo. So, as we have seen during this presentation, both Danieli systems for the waste heat recovery are flexible systems, have a flexible configuration, due to the fact that it's possible to choose the design of these systems according to the different necessities. They are both designed to mitigate the discontinuous process of the electric arc furnace, thanks to their accumulation system, the steam accumulator in one case and the hot water accumulator in the other case. And they are both maintenance-friendly solutions because the activities to be done on these systems are basically just regular controls and the standard periodical maintenance to be done during the scheduled shutdown. Then, in case of special requirements of the customers, it's possible to further increase this maintenance-friendly concept by installing, for example, a bypass line in case of installation of a boiler or a heat exchanger, in order to allow the maintenance activities, additional maintenance activities, if any, on this equipment without stopping the steel production. And this is possible, for example, installing a quenching tower in the bypass line, so the primary fumes cooling is anyway provided, with also the additional beneficial effects given by the fast cooling provided by the quenching tower itself. And in Danieli, spoiler alert for the next presentation, we have developed several interesting configurations for the quenching tower. You know, all these features are nice. Yes, I can choose whatever configuration I want. Yes, I can be flexible in many design features. I can decide to produce steam or electrical energy. All true. Good marketing stuff, by the way. But at the end of the day, what really matters is that with Danieli waste heat recovery systems, you can save money and reduce the environmental impact by lowering the carbon footprints of your plants. And these are the real key features that we're sure all of you are looking for. Thank you all very much.
Thank you very much.
Okay, let's see the questions of our customers. Please, show first question. What is the indicative time for the supply of a waste heat recovery system?
Okay. Okay, I can answer that. Okay, thanks for this question. Good question. Let me say the answer, of course, depends on the kind of system you want to install and the configuration of the system you want to install. So, for example, if you are recovering the energy only from the cooled parts or also from the boiler or the heat exchanger. But if we have to give let's say an indicative indication about the lead time, it could be from 12-13 months